Right, let's see. Session one, what we would discuss today is mostly about how the mole concept is used as an application. Okay. So the first term you need to know is basic unit conversions, right? When it comes to pressure, the terms like atmosphere, bar, Newton per meter square, centimeter of Hg column, millimeter of Hg column, and torr or torricelli. These are the different units we will be observing. The relation between them includes one ATM is approximately 1.01325 bar, or that if you write in terms of Pascal, another 10 raised to power of 5 will be multiplied to it. And as a kilopascals, it is 101.325. That is the kilopascal value. 1 bar is approximately 100 kilopascal or 10 raised to power of 5 Pascal. ATM can also be related as the raise in the mercury column in the barometer, and that is around 76 centimeters of mercury or 760 of mercury. Another terminology that you will be using is torricelli unit, which is 760 torr. These are basic pressure units. As it comes to volume units, you will notice that it will be liter, decimeter cube, meter cube, and centimeter, ml. These are all the units that will be used. And 1 ml is typically same as 1 centimeter cube or 10 raised to power of minus 3 liters. And 1 decimeter cube is 1 liter, which is 10 raised to power of minus 3 meter cube. Got it?
Yes, sir.
Temperature wise, the relation is between these three units: degree Celsius, Kelvin, and degree Fahrenheit. So, Kelvins is degree Celsius plus 273.15, while degree Celsius is 5 by 9 times of degree Fahrenheit minus 32. Okay. So, this is something which I would suggest you to remember and write it down. Got it? Next, if it comes to length or distance, typically we measure them in centimeters, millimeters, meters. But more than that, because we are going into a minuscule scale, you will come across 1 centimeter, which is approximately 10 raised to power of 8 Armstrong units. Okay. And 1 meter is also equal to 10 raised to power of 9 nanometers. And 1 meter is also equal to 10 raised to power of minus 6 micrometer. And 1 meter is also equal to 10 raised to power of minus 12 picometer. Okay. That also implies that 1 meter is 10 raised to power of, sorry, 12. 10 raised to power of 10 Armstrong units. Okay. So this is another important conversion which we'll be using it a lot of times. Okay. In fact, 1 meter is also equal to 10 raised to power of 15 Fermi units, but that is rarely used. The most used terminologies are Armstrong units, nanometers, and picometers. Okay.
So, what is Fermi unit used for?
Fermi unit is again used for measuring extremely small lengths like distance of radius of the nucleus. Okay. Radius of the nucleus is approximately 1 Fermi unit. Got it? Distance between the uh, if it comes to quantum level, if you want to identify the distance between the quarks, got it, that is again used in Fermi levels, right? So Fermi is more related to quantum mechanics when you learn it in that level, right, where the distance is extremely small. That's where Fermi is more appreciated. Okay, right. Next, as it comes to definition of mole now, let me directly dig into that. Okay. So when it comes to definition of mole, right, In simple sense, mole is a number unit. So which is 1 mole is approximately equal to Na quantities or entities, whichever is the factor that you will take. What is Na? Na is named as Avogadro's number. Avogadro's number. Okay. And how much is that number relevant to? It is 6.023 into 10 raised to power of 23 entities. Okay. And while Na, or sometimes used as No, this is Avogadro's number, correct? Which I will relate it here. So 1 Na or 1 No is approximately this value. Okay. As a definition, if you notice, correct, it is defined as the amount of substance, amount of substance which contains as many entities as many entities as exactly present in exactly atoms present in atoms present in 12 grams of carbon 12 isotope. This is by definition. Okay. So if you need to check out what is the definition of mole, this is what it is. So if I take 12 grams of carbon 12 isotope, as many number of atoms that are present in it, pure carbon, if you take, that defines the mole. Got it? This is by definition. Okay. Now, according to spectrography, that is mass spectrography, sorry, or mass spectrometry. I can use the terminology as metry because I'm using more of metric term here. Mass spectrography reveals that mass of one carbon is approximately 1.99 into 10 raised to power of minus 23 grams. Okay, this is the mass of one carbon atom. So if I have to check number of carbon atoms, I would be writing this as total mass of carbon atoms carbon atoms divided by mass of one carbon atom, isn't it? This is how we can define it. So for example, if I take the total mass as 12 grams, right, that is what we have been defining, and that divided by 1.99 into 10 raised to power of minus 23 grams, which is the mass of one carbon atom. And this value turns out to be 6.023 into 10 raised to power of 23, which we define it as Avogadro's number n. This makes sense? Any doubt here?
No, sir.
Right. Now, one mole is again categorized into multiple terminologies. Got it? For example, if we take it in this form, that is terms like gram atom, okay, or terms like gram molecule, and another term that is used is gram ion. Here we are trying to relate the same moles, right, in terms of the masses here. So 1 mole when I'm writing, or simply I'll write it as mole. Okay. So mole can be again categorized into these terms: gram atom, gram molecule, or gram ion. Okay. What is the difference here? See, when I use the terminology 1 gram atom, which I meant one mole of that particular atom. Okay. So here the relation is about 1 mole of an atom. While here this is about 1 mole of molecule, 1 mole of molecule, or here it is about 1 mole of ions which we are taking. Okay, this is what it meant. To be more precise here, check this one. So if I write 1 gram atom of oxygen, suppose if I write it like this, 1 gram oxygen, which means I'm talking about 1 mole of oxygen atoms, which is Avogadro number of atoms of oxygen. Does it make sense? Very good.
Yes.
So, if I use the terminology 1 gram molecule on the other hand of oxygen, then I am referring to 1 mole of O2 molecule. I am referring to O2 molecule. And O2 molecule implies that I have Na molecules of Na number of molecules of O2, or this also implies that it has 2Na atoms of oxygen atoms, which also implies it has 2 gram atoms of 2 gram atoms of oxygen atoms. Clear? So 1 gram of molecule is also related to 2 gram atoms of oxygen atom. Is this clear, beta?
Yes.
Likewise, I can also use the terminology 1 gram ion of sodium. For instance, if I use that term, I meant here 1 mole of Na plus ions, which implies Avogadro number of sodium ions, Na sodium plus ions. Okay, is this terminology clear? So
Yes.
this is the first distinction of mole that we need to relate. Okay, the second important terminology that you will be using, right, during the mole is atomic mass unit, or also known as unified mass. Okay, the abbreviation that we will be using here is AMU, or simply U. Got it? Again, by definition, that is, it is defined as the 1/12th, defined as the 1/12th mass of, okay, 1/12th mass of 1/12th mass of uh, carbon 12 isotope, 1/12th mass of carbon 12 isotope, which is 1 AMU is equal to 1 by 12 into mass of carbon atom. And what was the mass of carbon atom which we identified? It was 1.99 into 10 raised to power of minus 23 grams. And this value comes out to be 1.67 approximately into 10 raised to power of 24 grams. Okay. Or if you write that in kgs, it is 10 raised to power of minus 27 kgs. Clear?
Yeah.
In short, 1 AMU is also the reverse of Avogadro's number, isn't it? Because That is what we exactly did as the definition of mole, 12 by 1.99 into 10 raised to power of minus 23.
Mm.
Got it?
Yes.
So this relation is important, that 1 AMU multiplied by Avogadro's number will always fetch you 1 gram. Okay, this you should note. Done?
Yes, sir.
Now, important thing to note here is that an atomic mass by definition is mass of one atom, one atom expressed in AMU, one atom expressed in AMU. Okay, so hydrogen is 1 AMU, which is 1.66 into 10 raised to power of minus 24 grams, while oxygen 16.8 is a representation, which is 16 AMU, which is 16 times of 1.66 into 10 raised to power of minus 24 grams. Likewise, if you take uh, nitrogen, this is 14 AMU, which is 14 into 1.66 into 10 raised to power of minus 24 grams. Clear? Is this clear, beta?
Yes.
Now, in short, if it is about atomic scale, we use the terminology AMU. Okay. If it is a macroscopic scale, it would be better to represent in grams or kgs. Got it? That is what we are supposed to do. Clear on this point?
Yes.
Right. Let us understand the next term, which is molecular weight. Molecular weight. So basically, it is the mass of one molecule, one molecule expressed in AMU. Okay. So I'm sure you do understand. Suppose if I ask you carbon dioxide, you will be adding 12 plus 2 times of 16. That makes it 44 AMU. Got it? Now, there are few terms which are very essential for us to remember in terms of what are the molecular masses in AMU. Okay. So these are few things which you should practice it right now. So please check carbon dioxide. Other than that, we can have NaOH, which is very frequently asked, SO2, right? Then we have Br2. Then we have H2SO4, H3PO4, K, sorry, not K, NaHCO3, Na2CO3, calcium carbonate, H2CO3, which is oxalic acid, CH3COOH, which is acetic acid, CH3CH2OH, ethanol. Generally, alcohol means this is the first reference that should come to your mind. That means we are talking about ethanol. Okay, right. Let us quickly calculate together. Atomic mass of sodium is 23. Oxygen is 16. hydrogen is 1. That makes it 40 AMU, right? Next, sulfur is 32 plus 2 times of 16. That makes it 64 AMU. 1 bromine is 80, which makes it 160 AMU. Calcium carbonate is 40. Calcium is 40 plus carbon is 12 plus 3 times of 16. That comes to be 100. Okay, 100 AMU. Next, there are 2 carbons, so 2 into 12 plus there are 6 hydrogens plus 16. Okay, so that is 46 AMU. Hydrogen 2 plus 32 plus 4 times of 16, that comes to be 98 AMU. H3PO4 on the other hand is also same. Remember, phosphorus usually students tend to forget, it is 31. Okay, plus 4 times of 16. So that is again going to come out as 18 AMU. Sodium is 23 plus 1, 24 plus 12, which is 36 plus 48. Okay. So how much it is? 84. Next, Na2CO3, 23 into 2 plus 12 plus 48, which comes to be 106 AMU. While H2CO3, this is 2 plus 2 times of 12 plus 48. Okay. So that is 50 plus 24. So how much it is? 74 AMU. Lastly, we have acetic acid, which is 12 plus 4 plus 32. Okay. Sorry, not 12, 24. 2 carbons, so 24 plus 2. So total it is 60 AMU. You see clear, beta?
Sir, we have to learn these weights, right? Like of singular elements.
To some extent, got it. As in when we keep going across the questions, slowly we'll start learning it. So that's why I'm not separately getting into that sheet or anything. Okay. Hmm.
Sir,
Shall we go ahead? Did you finish?
no, sir.
Yeah, finish them. Next, we got an idea that what exactly is the molecular weight used for. Okay. In general, right, check it out. In general, okay, atomic mass is precisely mass of protons plus mass of neutrons plus mass of electrons, isn't it? Because these are the subatomic particles, we expect them to be present. If you compare the relation of these three, you will notice that the mass of proton is approximately 1.66 into 10 raised to power of minus 24 grams. Mass of neutron is 1.667 into 10 raised to power of minus 24 grams. While mass of electron, however, comes out to be 9.1 into 10 raised to power of minus 27 grams. which clearly suggests that the value of electron is too small. In fact, mass of proton is approximately 1836 times that of mass of electron. Important information. Okay. That mass of proton is approximately this much. Hence, if you compare the atomic mass in general, you will notice that the mass of electron is ignored in front of these two. So that's why we write atomic mass is approximately equal to summation of all the protons plus summation of all the neutrons, correct? This entire thing multiplied by mass of either proton or neutron. Here we are considering that the mass of proton and mass of neutron is one and the same. And this summation is what we call it as number of nucleons. Okay, this is nucleons multiplied by mass of proton. So Nu is called as number of nucleons. So nucleons basically is number of protons plus number of neutrons, assuming that their mass is almost the same. Is it clear?
So,
Going ahead, we'll slowly get to the idea that how much is the number of protons also present in it. Okay, that is the notation we will learn it. Correct? Now, keeping that into mind, suppose in case if at all I add what is the mass of ions. Suppose if I ask you what is the mass of ions, correct? For instance, if I ask you SO4 2 minus mass, right? To be precise, if you have to calculate the molecular weight of SO4 2 minus, I should be looking into first the sulfur. So within the sulfur, we have to check out mass of one proton into 16 protons plus mass of neutron into 16 neutrons plus mass of sulfur into 16 electrons. Sorry, mass of electron into 16 electrons. This is how we are supposed to check, isn't it? And again, this should be done with 4 times of mass of proton into 8, which is the oxygen, plus mass of neutron into 8, which is of oxygen, mass of electron into 8, which is number of oxygen. And then we have to again multiply 2 times of mass of electron into that's it, 2 times of mass of electron. Why is that so? Because there is 2 minus here. The 2 minus means this is how much we have to add. Precisely, this is how much we need to add, correct? But what do? We ignore the mass of electron here, here, and here. So even in the ions, eventually you are only adding the mass of proton and neutron. So it doesn't matter whether the overall molecule carries a positive charge or a negative charge. You're just simply supposed to find out the mass of proton and neutron together. And that's the reason why we will add here. And we also assume that the mass of proton and neutron are same. So it is as if you are finding out the atomic weight only. So you can see it is like 32, which we have combined it as proton and neutron, plus 4 times of 8, which is again combined of all the neutrons and protons for oxygen, and that multiplied by, sorry, uh, 4 into 16, not 8. I mean 16. 8 plus 8 is 16. And that is what we need to multiply. And total that you will get is 96 AMU. Is this clear, beta?
yes.
So it doesn't matter even when it comes to ions. We are only supposed to find out mass of uh, protons and neutrons only. Another such example, if you notice, CO3 2 minus. So for that also, it is about 12 AMU plus 48 AMU. ignore those two minus. So that makes it 60 AMU. Okay. Even if you have a positive value, NH4 plus, so that is 14 plus 4, so total 18 AMU. Or even if you have H3O plus, okay, so here also it is 3 plus 16, so which is 19 AMU. Okay, so this is how you can identify the mass of atoms as well.
So what
Clear?
is H3O?
H3O plus.
What is it?
Usually, when it comes to water, I'll put it as a note here. Usually, when it comes to water, you know, if if there is some acid being added to water, so the acid is the one which releases H plus, and this H plus is so strongly bound to water, it always appears or isolates as H3O plus. Got it?
Yes, sir.
So we call it as hydronium ion. Okay. Remember these terms, going ahead, we will be again discussing about the name culture. How do we use that? What is the name of every different element? But as of now, since we are on this stage, you can remember H plus is always used as a term proton. It has nothing but one proton. That's why a proton is always referred as H plus.
Yes.
And OH minus is referred as hydroxyl. OH minus is referred as hydroxyl. On the similar term, you can see NH4 plus is ammonium. Ammonium. In fact, whenever you have a positive ion, it will always end with em. That is the reason why I call it as hydronium. Okay. Right. Now let's get back to the term. Next term is about relative relative atomic mass. Relative atomic mass, RAM. Got it? Relative atomic mass. It is the it is the relative mass of is the relative mass of an element with respect to 1 AMU. Okay, it is dimensionless because it is a relative value, so it is dimensionless. And as a formula, how do I write? RAM is equal to mass of one atom in AMU, that divided by mass of one atom in AMU, and that divided by 1 AMU. Okay. So in short, if I want to calculate the mass of one atom, I can simply multiply this with RAM into 1 AMU value. This is called relative atomic mass. And likewise, I have another term, relative molecular mass. Relative molecular mass, RMM. So it is the same thing. By definition, you can see, I can just copy this part here. So it is relative mass of an molecule, of a molecule with respect to 1 AMU. So these terms are all the same here. So it is mass of one molecule. That's the only difference. Clear? And you know that when we express that mass in grams, now instead of AMU, if you express that in grams, then you will make this one AMU into 1.67 into 10 raised to minus 23 times. Okay, right. So that's the idea you need to have it from relative atomic mass or relative molar mass. Whatever we have calculated earlier is all relative atomic mass only. Okay. Now we use this term more often here. That is, what is molar mass? We'll be using this a lot of times. What is molar mass? So please check it out. In general, whenever you use the term molar mass, it's a very generic term. Okay. Molar mass refers to both terms, that is, molar mass of any species. It could be an atom, molecule, ion, or anything. So that is mass of mass of 1 mole of a species. Correct? And now this species could be an atom, it could be a molecule, it could be an ion. Okay, which means if you ask the terms like molar mass of electron, suppose if I ask you what is molar mass of electron, right? So it is simply mass of electron multiplied by Avogadro's number. That's it, because you are doing it for 1 mole. All right. Mass of electron is 9.1 into 10 raised to power of minus 31. If at all I write that in kgs, multiplied by Avogadro number is 6.023 into 10 raised to power of 23 per mole. Okay. So what I would get here is, if I remove this kg, the units what I get is kg per mole. This is the value of molar mass. So the units generally for molar mass will be either gram per mole or kg per mole. Okay. So if I put all of this value, in fact, this comes to be 96500. This is the value, kg per mole. We'll be using this as a reference known as 1 Faraday or simply 1 farad. Okay. So 1 mole of electron is always equal to how much charge? 1 Faraday charge. Likewise, I can use what is the molar mass of O2 gas. That means I'm referring to mass of one molecule, preferably write it in grams, correct? Sorry, preferably write it in AMU, and then you can convert that into grams, correct? So that into Avogadro's number, correct? And you know that this is 32 AMU into Na. Do you remember this value? 1 AMU into 1 Na is equal to 1 gram. Hmm?
Yes,
So gram per mole. So therefore, this is going to be 32 gram per mole. Okay. So that becomes the molar mass of O2. Got it? Now, molar mass can be categorized into two parts. Molar mass can be categorized into two parts. One is gram atomic mass. Gram atomic mass, GAM. And the second term we'll be using is gram molecular mass. Gram molecular mass, GMM. So in short, whenever I use the word GAM, that means I'm referring to, atomic mass of it, right? Atomic mass per mole. For 1 mole, how much it is. Correct? If I put it like a simple table here, beta, now let's see. Suppose I add something like He, helium, nitrogen, oxygen, argon. Okay. So for this case, if I ask you first what is atomic mass, then you will write it as 4 AMU. Here it is 14 AMU. Here it is 16 AMU. Here it is 40 AMU. These are the atomic masses. If I ask you what is relative atomic mass, you just remove that AMU term. That is relative atomic mass, correct?
So,
And if I ask you gram atomic mass, that means now you will write the same thing as gram per mole. 14 gram per mole. This is 16 gram per mole. And this is 40 gram per mole.
sir,
Yes, beta.
can we say that one atomic unit is equal to 1 gram per mole?
Yes, absolutely. Not equal to, equivalent to, because that
Equivalent.
is for one atom, this is for one mole. Yeah. So it is equivalent to, not equal to. Similarly, I can add some molecules like, let's say, carbon dioxide and H2O. So for such cases, you will be writing what is molecular mass. Molecular mass, you will write it as 44 AMU. This is as 18 AMU. And relative molecular mass is 44 and 18. And GMM, which is gram molecular mass, which means it is 44 gram per mole, and here it is 18 gram per mole. I think it all makes sense.
Yes.
Right. Now let's look into this simple question that could be asked. Okay. This was a previous year question which was asked like this. Find the molar mass of a cylindrical virus of dimensions, length, radius, and density are given. Okay. So let's do it together, beta. So how we can solve? First, I'm sure you do understand that cylindrical
Yes, sir.
means,
Cylinder.
right. So this is the cylindrical form here. Sorry, second. Like this. This is a cylindrical form here. Now here, this will be the radius part, and this is the length part. Okay. And length is given as 170
And strong unit.
Armstrongs, and radius is given as 35 Armstrong unit. Volume of a cylinder is, you know,
I square
4
H.
by 3, sorry, pi r square L, pi r square L, right? So you work it out better. Right? We know the details of the volume, so I'm sure you can put that values here. So you'll get this as 22 by 7 multiplied by 35 into 10 raised to power of minus 8. I'm trying to write everything in grams, beta. That's why I'm putting, you can see the density is given in gram per ml. That's why I'm trying to produce everything in grams. So this into 170 into 10 raised to power of minus 8 centimeter again. That multiplied by, that's it. So 4 pi r square here. So this square. Okay. So that's approximately coming out to be 22.7 into 35 whole square into 170 into 10 raised to power of minus 24, uh, 24 centimeter cube, okay, or cc.
So this will be 2805 double zero into 10 raised to minus 24.
Correct. 2805 into 10 raised to power of minus 24. Hmm. Right. So this is the centimeter cube value. So what is the mass here? We get mass is equal to volume into density. So 2805 into 10 raised to power of minus 24 into density, which is 0.8. Okay. Check if you are getting the closest value here. So 2805.
Sir, wait,
So this is coming as 2244
four
into 10
four
raised
into
to
10
power of
raised to
minus
minus
24
24.
grams.
Yes,
Yeah.
sir. Yes, sir.
Now you got the mass. Can I say that this is the mass of one? This is the mass of one virus molecule. Correct. If this is the mass of one viral molecule, what is the molecular weight? So molecular weight is always referring to gram molecular weight. Even if it's not given, you should always think in terms of gram molecular weight. So therefore, it is supposed to be 2244 into 10 raised to power of minus 24, right? That multiplied by Avogadro's number. So 6.023 into
Yes,
10 raised to power of minus, sorry, plus 23 grams. Here, gram per mole. Sorry, this is, yeah, gram per mole. I mean, this is not gram per mole. This is just a number per mole. Okay. Yeah. So now if you multiply this value, you will get it as 2244. So 2244 multiplied by 6.023. So that is coming as 13, 1351 5.6 into 10 raised to power of minus 1. So which is 13, 15, 15, 1.56, gram per mole. So this is the molecular mass.
yes, sir.
Is this value clear?
Yes. Sir, these
Right.
multiplication values are very big, sir.
It will get, I mean, slowly you will get an habit of it. Okay. But nevertheless, I will suggest, like, sometimes in the middle, we can have some Vedic math sessions also, just to make sure that the calculation becomes much faster. Got it? So, what happens, you should be able to figure out the approximations faster. Okay. You should not worry just by watching the number. Okay. That fear should not be there. Yeah. Mm. Now, let's see if the question is asked in a different way. Okay. So, what if the question is asked in this sense that in a molecular compound, it contains two atoms of carbons, three atoms of oxygen, and these many number of unknown element. Find the molecular mass in AMU. Okay. In this particular direction, if the question is being asked, then how do we get to this? Now, check it out. You know that carbon, we have two atoms. Yeah. Which means it is 2 into 12 AMU. That is a mass of two carbons. While oxygen, we have three atoms, which is, 3 into 16, which makes it 48 AMU. Now, supposed to figure out how much is the AMU value here. And you know that X is some element here, and it has 1.67 into 10 raised to power of minus 23 grams, right? So, how do we figure out the mass in AMU? So we just have to multiply, we just have to divide it by, correct? 1.67 into 10 raised to power of minus 23. That grams divided by 1.67 into 10 raised to power of minus 24, correct?
One atomic
That is
mass.
in AMU. So which is 10 AMU. So this is some new element which has an atomic mass as 10 AMU. So that makes it molecular mass. Molecular mass relates to 82 AMU, correct? So which is,
Yes,
this
sir.
one is 24 plus 48 plus sorry, plus 10. So that makes it 82. Okay. If I ask you what is a gram molecular mass, in that case, it will be 82 gram per mole. That should be the value. I hope this makes sense.
Yes.
Right. So this is the first bit of it that we need to know. Okay. Now, before jumping on to the next part of it, got it, which is about identifying, average molecular mass. Got it? Yeah. Now, let's see how to figure out what is the average molecular mass. Okay, this is a new important term that we should be uh, familiar with. Got it? Now, before getting into that terminology, another important term we got to realize is whenever we talk about density terminology, what are all the terms we use? Okay, check out when it is density, D, correct? Density in simple terms is ratio of mass and volume of a species. Correct? This is the simple terminology. Now it is categorized into multiple terms. One is absolute density. One is absolute density. Absolute density is the one which we usually write it as D, and that is by definition mass by volume. So whatever we have writing as a density, it is usually mass by volume. The units, however, are gram per ml or gram per cc or gram per liter or kg. You can write it as kg per liter or kg per meter cube. These are all the terms which we will be using. Then we have another term, relative density. Relative density. Okay. Let us write it as RD. So relative density, right? Here, this is by definition, it is density of a species, whichever the species you would decide or define, that divided by
Density of water.
density of some standard species. Now, again, this standardization is different in different terms. Got it? Standardization in liquids. So, first in liquids. So, in liquids, clear, relative density is, often used as specific gravity. We use the term specific gravity. In physics, you might see this as SPGR. Yeah, specific gravity. So here, SPGR is basically density of liquid solution, whichever we are taking in gram per ml, that with respect to 1 gram per ml. Okay, this is 1 gram per ml. But what is this 1 gram exactly? Where is it coming from? It is coming from density of water. So it
Yes.
is density of water, and water precisely shows, you know,
Yeah.
1 gram per ml at 4 degrees Celsius. ठीक है बेटा? Next. In gases, whenever it comes to gases, now the relative density is often used as vapor density. The terminology more often used is vapor density. Okay. Now, what does this vapor density mean? See, vapor density of a gas relates to density of a gas at constant pressure and temperature divided by density of hydrogen gas at same constant pressure and temperature. Okay, this is by definition. So it is simply like density of a gas divided by density of hydrogen, and this at constant temperature and pressure. Got it?
Yes, sir.
Let me bring one important terminology here, especially in gases. Okay, whenever it comes to gases, you should be able to often relate that gases can be again of many types, but most of the time we refer gases for a perfect gas, which is Okay, an ideal gas, an ideal gas is most used for defining defining
Yeah.
various formulas. Okay,
Yeah.
and for an ideal gas, if you remember, we discussed about that. An ideal gas is simply PV is equal to nRT, which it follows. Okay, so that means
The
yes,
writing is not showing on the screen.
we are writing.
The writing is not showing on the screen.
Okay, specially we use PV is equal to nRT, which we call it as ideal gas equation. This is used as ideal gas equation. Now, in this ideal gas equation, what if I take the volume term to the right hand side? You will get this term. And you know that by definition, what can I write about number of moles? You see, number of moles of a gas can often be written as, mass of gas divided by, right, divided by molecular weight of gas or gram molecular weight of the gas. This is by definition what we can write it as number of moles. Okay. So in such case, if I write this number of moles as mass, which is weight divided by molecular weight into volume into RT. Now, weight by volume is what we define as density. So this will become density of a gas RT divided by molecular weight. Okay. And molecular weight, henceforth, I'll refer it as capital M. We refer it as capital M. Okay. So from here, I get this definition that the density of an ideal gas can be related as Pm by RT, which implies density of a gas is directly proportional to molar mass of a gas. Correct?
Yes, sir.
Now, if I write what is vapor density, you can see vapor density is density of a gas divided by density of hydrogen and at constant temperature and pressure. So that means these terms will anyway get cancelled. So it will become molar mass of a gas by molar mass of hydrogen. And molar mass of hydrogen is something which we know, that is 2. Therefore, vapor density is a relative density. For any gas, it is defined as molecular weight of that gas divided by 2. So this is another important formula that you should remember. Okay, how we relate vapor density with respect to vapor density with respect to molar mass. Okay.
Is vapor density also unitless?
Yes, it is dimensionless because it is relative term. That okay? Now, what if I ask you these terms here? Okay, that what will be the vapor density of the gas compound, which is COX, is found to be 14. You need to find out the value of X. By definition, vapor density is
So
molar mass, which is
uh,
X times of 12 plus 16. Correct?
1, 2.
Correct. So that divided by 2, because that will be the molar mass of hydrogen. So 14. So that is, sorry.
X is equal to 1.
Correct. So 28 into X is equal to 28. So X is equal to 1. So this is about carbon monoxide, right? Is that okay?
So
Right. See the next one. What if I need to figure out what is the relative density of an unknown gas compound with respect to oxygen atom is 4. With respect to oxygen atom is 4. Find the molar mass of the gas. Now the definition is being changed. What if the vapor density is defined as the density of a gas divided by density of oxygen gas? In such case, what will be the molecular weight beta? Check out. Now I can write vapor density of a gas by definition here is density of a gas divided by density of oxygen at constant temperature and pressure. Okay, so that means it is molar mass of a gas divided by molar mass of oxygen at constant temperature and pressure, correct? And that is given as 4. So molar mass of a gas is equal to 4 times of molar mass of oxygen. Okay, so molar mass of oxygen is how much? 32 into 4 times. Clear? So how much it is? 128 grams per mole. So it all depends upon by what atom or molecule you are defining. Okay. Is this logic clear, beta?
yes, sir.
Now let's go and understand the next terminology. What is average atomic mass? And how do we define this average atomic mass or average molecular mass? First, let's focus on to this terminology, average atomic mass. Well, it is calculated due to presence of presence of isotopes presence of isotopes. What exactly it is? See, for example, if it comes to hydrogen atom, okay, hydrogen atom in nature exists as three different types. One is called protium, the other one is deuterium, the third one is tritium. Okay, now these forms are called isotopic form. So first you need to understand a general notation of an element. If you have an element, what is the general notation? The general notation is like this: x, any element x with uh, a and z. This is the general notation, a and z, where a represents mass number which refers to number of protons plus number of neutrons. Okay, and z represents atomic number which represents number of protons or number of electrons in neutral state. Okay, this is by definition.
Sir,
And
state?
why?
Why in the neutral state?
Because if you have something like x2 minus, which means now we have more number of electrons compared to that of protons, right? So then these two will not be same, isn't it? These two numbers will be only same when they are in the neutral state. That means when they do not have any charge. When they have any charge, that is positive or negative charge, that means the number of electrons are differed compared to the number of protons. So we come across these definitions or these terms which we use very often. One is isotopes. Isotopes. Isotopes means we should have same same atomic number
A
but
different.
different mass number. Okay, so and that's what we see these examples as. For example, if it comes to hydrogen, we have H11, H21, H31. Got it? When it comes to carbon, we have carbon 1216, carbon 1316, carbon 1416. Likewise, if it comes to oxygen, we have 16.8, oxygen 18.8. 17.8 also there. We use very less like. If it comes to chlorine, okay, chlorine, we have 35, 17. We have 37, 17. So like this, for every different element, you may have different isotopes present with it. Okay. And their composition may be different in atmosphere. For example, in nature, if you compare the hydrogens here, 99.9% will be hydrogen, that is protium. The second one has a name, deuterium. So that will be hardly something like 0.1 percentage. And this will be extremely low. So 10 raised to power of minus 8 percentage, that low. So you can see very, very small composition. These are isotopes. Then we have isobars. Isobars, which means we have same atomic, same mass number, but different, right, Z value. Got it? So if you check out the examples here, for instance, potassium, correct, can be 40 and 90. Calcium can be 40 and 20. Argon can be 40 and 18, right? So these are isobars. Likewise, we can have carbon with 14 and 6, nitrogen as 14 and 7. So these two are also isobars. Got it?
Yeah, yes, sir.
So I guess this definition is clear, better. Right. Next one is isotones. Come across this isotones. Okay. So isotones is about same number of nucleons. Got it? Sorry.
Welcome to Chemistry
Sorry.
Academy.
So when it comes to isotones here, so they should have same number of neutrons. Same number of neutrons. As the same number of neutrons means A minus Z value, isn't it? If you have A minus Z value, that means they are all isotones here. Correct. If you notice this example, for example, if you have silicon, okay, silicon, we have 30 and 14. Phosphorus, we have 31 and 15. And sulfur, we have 32 and 16. Now you notice that A minus Z value is 16 only in all the cases. So these three are isotones. Yeah. I think these terms are clear, better.
Yes, sir.
Last one is isoelectric species, sorry, electronic species, which means elements having same number of electrons in atoms or same number of valence electrons in molecular form. If you are talking about molecules, you need to check out same number of valence electrons. If you are talking about the atoms, that means you should check out the total number of electrons. For instance, if you take it carbon 4 minus, nitrogen 3 minus, oxygen 2 minus, and fluorine minus, neon, and then sodium plus, magnesium 2 plus, and aluminium 3 plus. If you notice the number of protons, here there are 6, 7, 8, 9, 10, 11, 12, 13. While if you compare the number of electrons, all of them will have same number of electrons, which is 10 electrons. So that implies all these are isoelectronic species. Is that idea clear, beta?
Yes, sir.
Okay. So now coming to the average value. No, let's get back to this original term what we are discussing, which is about what is average. Okay, atomic average and molecular average. So usually how it is been asked, the when it comes to average atomic mass of an element, you just need to find out the weighted average. Okay, usually this data will be given like 10 5 boron, 11 5 boron, correct? It's mole percentage, that means how many moles, or volume percentage. Mole percentage, volume percentage is the same. So it is 20 and 80 given, and mole ratio, mole ratio given is mole ratio given is 1 and 4. This is what has been given. So in such case, how do we calculate the molecular atomic weight average? Atomic mass or atomic weight average is equal to, you check out the total mass that divided by total number of moles. That's how you'll check it out. Okay. So total mass is, there is one boron of 10 plus 4 borons of 11, that divided by, okay, 1 plus 4, correct? So either percentage is given or mole ratio is given. Both of them are one and the same. So if the percentage is given, you can do the same thing as percentages, that is 20 into 10 plus 80 into 11 divided by 20 plus 80, isn't it? That is one and the same. So it is going to come out as 54 by 5, which is 10.8 AMU. So is this definition clear?
Yes, sir.
Now, when it comes to chlorine, chlorine is 3517 and 3717. Now, here mole percentage is given as 75 and 25 percentage. This is the mole percentage. So, molecular weight average, atomic weight average is 75 into 75 into 35 plus 25 into 37, this whole divided by 75 plus 25, correct? So that comes to be 35.5 AMU. Yeah,
Yes, sir.
this one is clear, right? Now notice this question. Okay, so let's check this question now. The question is being asked as find out the matrix match of isotope 1, isotope 2, and average is given. Average is already given. And from there, you need to refer which percentage is more absolute here. Got it? And which percentage represents a correct value here. Okay. So let's go with the A first, right? So here, this value is given as Z minus 1 and this is Z plus 3. Okay. Isotope 1 has Z minus 1 and isotope 2 has Z plus 3. Okay. And average mass is Z. So which means this is the mass number we are talking about. Clear? These are all the atomic masses. So check out how we can solve the A bit. First, I'll solve the A bit. Okay. Let us say the percentage amount for isotope 1 and 2. Let this be X and 100 minus X. Correct? In that sense, can I write that Z value should be equal to X into Z minus 1 plus 100 minus X into
Plus
Z plus 3, and that total divided by 100. Make sense? That's what we need to do. So how much we are getting here now? Check out 100Z is equal to Zx minus X plus 100Z minus Zx plus 300 minus 3x. So you can see this Zx will get cancelled and you will have this as 400 minus 4x is equal to 100Z. Correct?
sir.
Sorry, this should also be Z, right?
So
Now, one
in
second. 100Z. Yeah, 100Z plus 300. Sorry. This is wrong. Let me rewrite that. So 100Z is equal to 300 plus 100Z minus 4x. Okay.
$25.
Yeah. So how much is that value we are getting across? So this 100Z will get cancelled, beta.
X is
So we are
equal
getting 300 is equal to 4x. So x is equal to how much?
to 75.
Correct. So by 4. So this is 75. Okay. So that means x is 75 percentage by mole, right? So because this percentage is by mole. So mole percentage here, what we got is 75 percentage of isotope 1 and 25 percentage of isotope 2, right? So this is what we need to check. So yes, so 25 percentage by mole composition here and 75 percentage by mole composition. So this P part seems to be correct. P part seems to be correct here. Okay. Can you do the same thing for B? Please try that. Check how much value you are getting. Very good. So B, for B part, we got mole percentage as 50% of 1 and 50% of 2. Correct? Yeah. Now notice this. What if I have to check out what is the mass percentage? What we got it is mole percentage, isn't it? Now if I have to fetch what is the mass percentage, what I will do, check it out. You know that I'll take 100 moles to start with. 100 moles of A. Okay. And then I calculate what is the total mass of it. Total mass. Okay. Now total mass will be including 100 moles multiplied by the molar mass. Correct. Molar mass is how much? Z here. Average given is Z. Okay. So that multiplied. So this much in grams. Correct. So this is the total mass. Then individually, if you compare, we have 70, 75 and 25. Correct. So 75 moles of first isotope. That means mass of first isotope includes 75 multiplied by its molar mass, which is Z minus 1 grams, right? And 25 moles of 2, which is mass of 2, that is equal to 25 into 25 into Z plus 3 grams, right? Now we got the individual masses and total masses. Can we calculate what is the percentage now? Correct. So therefore, so the percentage amount of mass 1 is equal to mass of 1 divided by total mass. Total mass is how much? 100 into Z. So this one is 75 into Z minus 1 divided by 100Z. Correct.
So that's
Hmm?
1 by
Into
so
100. Yeah. Into 100. Okay. Got it. And percentage mass of 2 will be equal to how much? So 25 into Z plus 3 divided by 100Z into 100. Okay. Right. So this is the value we get. So how much we are getting here? So 75 Z minus 1 by Z. And here we have
25.
25 Z plus 3 by 100. Sorry, by Z. Is that okay? This is the percentages we got. But you know that addition of these two percentages should be equal to 100.
Yes, sir.
So you use that, you can get what is the mass percentage, because you will get the Z value out of it. And from there, you can get what is the mass percentage on it. Clear, beta? So that's how you can fetch out the mass percentage as well. Okay. So I would suggest you try the next three of it and compare what is the mass percentage which you are getting. Okay. Now you need to also emphasize on this part. Is it possible to get mass percentage without dependency of Z or with dependency of Z? Okay. That is the option that is given clearly. Understood? Right. Not now. Okay. You can do it later, but I hope you understood what to do about it. Yeah.
Yes, sir.
Okay. Now, let's see how you calculate the average molecular mass. Now, this becomes very important during our regular solving of questions, right? So, what is average molecular mass? Okay. So, notice average molecular mass. Average molecular mass. Okay. So, which is M average here. Now, it is calculated in case of a mixture of gases, calculated for mixture of gases. Okay. And you know, volume percentage or mole percentage are same in gases. This is called Gay-Lussac's law. Okay. We'll learn more in details in gaseous state, but just this basic term we should understand. Okay. So let us check with some examples. Suppose Air has many compositions, but on an average, we say that 80% of the volume by volume of air is of nitrogen and 20 percentage by volume is of oxygen, right? So I need to find out what is the molecular weight of air. How much is the molecular weight of air? Okay. So what do we do? See, we calculate molecular weight average is equal to what is the total mass of this air divided by what is the total moles we have. Okay. And you know that molecular weight average is equal to 80 into 20 plus 20 into, sorry, 28 plus 20 into 32, because these are the atomic masses of nitrogen and oxygen. That divided by 80 plus 20, correct? So this is the molecular weight average. So which is coming out to be 2880 by 100. So what are we getting here, beta? 28.8 AMU. Sorry, molar mass. So it is gram per mole. So this is the gram molecular weight of air. Okay. Right. I'll give you one more example for you. Please do this one. Find average molecular weight of mixture having SO2, O2 and helium. This is 128 grams given, 64 grams given, 8 grams given. This is the mass given. Directly mass formula is given, so you can calculate from there. Okay. So start working on it. Another question which you need to find out is SO2, O2 and helium with mole ratio. That is given as 1, 1 and 3. Try these two. Here, I have written the solution for your comparison. Please check if you are getting the same thing.
I was still calculation of first question.
Okay, complete that, and refer the answer whether you're getting it right. Next, notice this is a typically, next thing you need to notice is how in gases a terminology called STP and NTP is very, very often used. Okay, so that is STP and NTP conditions. Okay, so first one, STP. STP is used when 1 mole of an ideal gas is present at pressure of 1 atm, temperature of 0 degrees Celsius or 273 kelvins, then volume occupied by the gas is 22.4 liters. Okay, this is STP condition. Got it? In fact, actually speaking, this is not STP. This is more used as NTP, because earlier it was used as STP. Now it is used as NTP. Now, as it comes to STP, the definition pretty much goes the same here. The definition almost goes the same here. except instead of ATM, here it is a bar pressure. Sorry, instead of temperature, okay. Sorry, yeah, that's correct. Instead of this ATM, now we have a bar pressure. So when you have this as a bar pressure, then we will get this as 22.7 liters. Okay. So just this condition is what you need to understand. At this condition, what would be the case? Correct. So based on this, how the questions can be framed is to calculate the total volume of the gas or volume of the mixture. Okay. So find volume of the mixture containing mixture containing okay 2 gram molecules 2 gram molecules of hydrogen, 2 gram atoms 2 gram atoms of helium, 88 grams of carbon dioxide. Okay, 88 grams of carbon dioxide, and simply 20 grams of neon 20 grams of neon. Okay, 64 grams of oxygen. Okay, and 5 moles of nitrogen. So if you have the mixture of all of this, in such case, first you need to convert everything into number of moles first. So you can see number of moles of hydrogen. How many we have? 2, correct? And number of moles of helium, also 2. Number of moles of carbon dioxide, which is 88 by 44, which is also 2. Number of moles of neon, okay? Neon, how much it is? 20 by 20, correct? Which is 1, okay? And number of moles of O2, 64 by 32, which is again 2. So number of moles of nitrogen, which is 5 already given. So that makes total number of moles is 2 plus 2 plus 2 plus 2 plus 1 plus 5. Correct? Right? So how much it is? 14 moles is what we have. Correct?
Yes.
Therefore, I can calculate what is the volume of mixture of gases. Volume of mixture of gases includes 14 times of 22.7 if it is mentioned as STP. While if it is mentioned as NTP, you will use it as 22.4. That's it. Clear? So 14 cross this will come across 317.8 liters. This much is the volume that has been occupied. Okay, beta. So based on the question, you need to figure out accordingly what kind of a volume you need to use. Okay. So sometimes if the volume itself is mentioned, you know what is the what is the number of moles it is carrying. Here, there is one more addition which I'll make as an extra thing, mole fraction. By definition, it is number of moles of a species, moles of species with respect to total number of moles, total number of moles. For instance, in this question, if I ask you what is a mole fraction of hydrogen gas, so what do? Hydrogen gas total are 2 moles here, isn't it? So that 2 divided by 14. So 1 by 7 is the mole fraction of hydrogen gas. Okay. So keep this in mind. These two terms, one is mole fraction term and one is the volume of the mixture at STP or volume of a gas in generally at STP and NTP. Okay. This would help us understand something called a Y map, okay, which is relation of all whatever we did. We are trying to relate everything at one place now. Okay, so that is the three corners of the Y. We have one, what is the mass of species in grams? Hmm? The other one being we have total total number of species, total number of species, okay, represented as n, okay, number of atoms, number of molecules, anything, and number of moles is what we are trying to relate in this y, uh, a y letter, with this being volume of ideal gas in liters. Okay, so this is one part. Second part, this is third part. Okay, so combining all these three, we will get what is the y part here. So that is one here. Yeah, these two are related like this. This one and this one are related like this. And here I have one more relation between these two. Okay. Now let's see if you have number of moles, correct? So here we are defining it as the number of moles and trying to relate with all these terms. So if this number of moles is multiplied by molar mass, okay, multiplied by molecular weight, then what do we get? Number of moles multiplied by molar mass will get the mass in grams, correct? And here, if you want to come across this one, you need to simply divide it by molecular weight. Molar mass by molecular weight will give you number of moles. Hmm? Number of moles multiplied by Avogadro's number will get total number of moles. Divided by Avogadro's number, we will get number of moles, right?
Yes, sir.
Volume, if at all I have divided by, okay, uh, molar volume, divided by molar volume. Molar volume is how much? 22.7 or 22.4 depending upon NTP or STP. And similarly, multiply this with molar volume, you will get what is the total volume of the gas. So this is what is Y map is. Okay. So this gives the gist of whatever we have studied. Ever see clear beta?
So,
Right. Now let's see how the questions typically are framed. Okay. First one, find number of electrons in the following: A, 32 AMU of CH4. Okay.
sir, I have to do
B,
this now.
huh?
I have to do this now.
You have to do it now. Yeah. So 1.6 grams CH4. C, 2.27 liters of CH4 gas, and D, 6.022 into 10 raised to power of 21 molecules of CH4. So if the question is asked in so many different formats, you should be able to figure out, what are the number of electrons in either of the cases. Okay, so try that. Let's see whether you're stuck it somewhere or is there anything going wrong at any place. See, total number of electrons in one methane, right, will be 6 electrons plus 4 electrons. So total 10 electrons are present, correct? In one CH4 molecule. And now, if you calculate the number of CH4 molecules, that will be equal to 32 divided by 16, which is 2 molecules. If one molecule have 10 electrons, so 2 molecules will have how many? 20 electrons. Does that make sense?
So,
Right. If you notice the second case here, you will see 1.6 grams, so which means number of moles is equal to 1.6 by 16, which is zero point 0.1 moles, right? Zero point 0.1 moles. So zero point 0.1 moles means number of electron moles in terms of moles will be equal to how many beta? 0.1 into 10. So which means 1 mole of electrons. 1 mole of electron. So 1 mole of electron is how many? Avogadro number. Okay.
yes,
And lastly, you can see number of electrons is simply equal to number of atoms or number of molecules in this case divided by Avogadro number of molecules. Correct? So which is number of, sorry, not number of electrons. This is number of methane in moles. How many moles we are getting? So we are getting it as 10 raised to power of minus 2 moles, right? So therefore, number of electrons in moles, number of electrons in moles, that includes 10 into 10 raised to power of minus 2, which is zero point 0.1 moles. So zero point 0.1 moles of electrons,
divide.
moles of electrons we have. So zero point 0.1 moles in terms of electron, in terms of the value is how much? This much. Right, beta? No?
Yes,